I've sectioned the talk into about 8, and from the contribution and progress, introduction, then the problem statement, the real-time solver formulation, onto the 1D application and 2D application, and then the 2D implementation of the work. Then I'm going to get into the conclusion. So to the contribution and progress of the work so far. One of the contributions of this work that I've done is in the algorithmic innovation. We reformulated LAMP with divide and conquer techniques, modal reduction, and Bayesian sampling to achieve milliseconds update speeds. Also, we achieved the experimental validation of this work. We demonstrated it on real systems, drove the experimental testbed. Also, the cross-domain applicability, that is, we tested it on 1D systems, 2D systems, and then we can apply it to several spectrum from aerospace to electronics. And lastly, the edge readiness. The work has been proven to run on hardware in the loop systems, so they are ready for embedded and cyber physical application. Now, during the course of my work, and during the course of my PhD, most of the work I'm presenting today have been published. We have presented them at conferences. So from the real-time server formulation to the 1D application part, we had like a publication, a journal publication, and some conference presentation. And also the 2D model formulation and implementation has also been published to and presented at conferences. Aside the work towards my dissertation, I've also been involved in several other projects during my PhD program, which one of it is the flexible electronics, which was directed towards my master's thesis. And we had a lot of good works in there with good publications, journal publications, and also conference presentation too. I've also worked on structural batteries during the course of my program, and we've also made very good, we had some very innovative work and project carried out there. So we had publications from there to and conference presentation. I also had a publication in additive manufacturing during the course of my program. So now I'll just get straight into my talk, like the basic part of my work. So to the introduction, aerodynamics. What is aerodynamics in the real world? So basically, if we look at the structure that we are seeing right here was exposed to blast, and the event of blast in the real world can be regarded to as aerodynamics. Now, another example of aerodynamic in the real world is when we have like a collision in vehicles. Airbag deployment, the event of airbag deployment can be regarded to as aerate. Also in space, where we have in-flight anomalies, like in space shuttles and area vehicles, as we can see in the figures here. Many of them are prone to in-flight anomalies that can be classified under aerodynamic event in the real world. So now, why do we regard to this event as being high rate? So the reason why we call them high rate is that they are very fast. They occur within a very short time. That is, their time is usually less than 100 milliseconds. And then they also have high amplitude in the sense that there's high acceleration accompanying this event, usually greater than 100 Gs. So here is a laboratory data that we can use to characterize high rate events in real world. So now if you look at this event, it lasted just about 0.2 milliseconds. That it's very fast. And then this event has a lot of large uncertainties in the external load. Aside that, there's high level of non-stationarity and heavy disturbances in the load. We can see the fluctuations in the data within just a very short period of time. And also, these results that we're seeing here generate a lot of unmodeled dynamics. There's a lot of unmodeled dynamics in the data in the sense that they do not conform to a particular like some kind of equation that you can use to like define the state of the of those events. So they are unmodeled in nature. So they are kind of difficult to track and estimate. So now, because of the difficulty and characteristics of aerodynamics, and because of how dangerous they can to people and to properties, we need to like estimate them and track this event in real time. So now, the problem statement, it's kind of difficult to track high rate dynamic events. So one of the challenge of tracking them is adequate sensing. There are not enough sensors available to track the systems, and also lack of system knowledge. Many researchers don't know about this event, so it can be difficult to track them because of lack of experience and knowledge, as well as high variability in loading. because of the unmodal dynamics that accompany this event and the different behaviors within that short period of time, it's also difficult to track them. And then we have limited resources for algorithm implementation. Because of how fast this event occurs in nature, we need to have like very fast algorithms to track and estimate this event. So we need to solve the system of equations accompanying this event very fast in order to estimate that. So here is my own main objective. This is where I come in to develop and formulate algorithms that we can use to like estimate this event within a very short time of about 1 milliseconds. So I'm working with a time constraint of 1 millisecond to solve the systems of equation for us to like estimate aerodynamic event. So now, there have been several methodologies for estimating irate events, one of which is physics-enhanced machine learning, and some people are working on that. And there's the real-time fusion of high-speed data augmented by model-based data, under which there's the finite element modeling method. And lastly, there's the uncertainty quantification method. My own work is based on a finite element modeling approach. So we are using a frequency-based approach to like track aerodynamic events to estimate the state of these systems. So you might hear me talking about frequencies, mode shapes, eigenvalues, and eigenvectors as I proceed in my talk. So we'll be using frequency of the system to track and estimate the structure of this. All right, so here is a result, a power result, FEA model updating result that was done before I started this work. And the orange line is the state of the system, the state of the roller position on the system, on the drop bed test bed that was used for this work. And the blue is the tracked state of the system. So we can see that we have a very close correlation between the original system and the tracked result. And from this result, it was obtained that the number of FEA nodes and the FEA models affect the error of estimation as well as the iteration time. So if the number of FEA node increases, the iteration time increases. However, the error is low. So we need to find a balance between the error and the iteration time. We need to look for an algorithm that can solve the system of equation while increasing the number of nodes so that we can achieve high accuracy and then also like fall under the time constraint of 1 milliseconds. So the generalized eigenvalue that was used for the power work that I just showed, we can see that it accurately estimates the state of the system. However, the result shows that the number of nodes used to define the system needs to be limited to 23. As you can see in this plot here, when the number of nodes goes above 100, above 23, the time taken to solve to update the system is more than 1 millisecond. But when it's constrained to 23, the time is we can achieve that 1 millisecond timing. But we already know that we need to increase the number of nodes to define the system to get accurate results. So therefore, there's need to formulate under solver to like carry out the estimation. So I'm going to talk about my work on real-time formulation now. So let's look at, I'll just explain structural dynamic modification. Let's look at this structure that we have here, simple one. And then if we had another structure to it, another simple structure to it to achieve this new structure that we're seeing here, the addition that is made to this system can be represented in terms of mass, stiffness, and damper. So we can represent modification to a structure in terms of the mass change, spring change, and spring and damping. So that's the basic concept of structural dynamic modification. Now, is it possible for us to use the existing frequencies and mode shape of an original structure to like predict the new frequencies and mode shapes due to the addition of mass and stiffness to it? Yeah, that's possible. That is the concept of eigenvalue modification procedure, where we have initial mass matrix, that's M1, and the initial stiffness matrix. And we're adding a change in mass or change in stiffness, that's delta M and delta K, to formulate the new equation of the system, which we can solve either by any approach that we want, either using the eigenvalue. We can compute the eigenvalue solution of this equation to get the new mode shapes and frequency of the system to define the state of this of the system. Now, when we talk about local eigenvalue modification procedure, it's a bit different from the eigenvalue itself. We are now talking about a singular change that is added to the system, which is not like adding both mass and stiffness. We're adding just one single change, either mass, stiffness, or damping at a time. So what LEM does is that it identifies the physical changes to the system, such as mass, stiffness, or damping, and then represent them in terms of frequencies or mode shape. And then it kind of models the altered state as a mixture of the initial state and changes that's made to the state. I'll explain that now. So what LEM does is to like look at the initial state of the system, identify all the participating modes, and then it uses those mode to like form the new state, like the altered mode, the altered state of the system. So it checks for people. Okay, let me just explain. Now, for all the modes in the initial state, they have different participating factor. They don't contribute equally. So LEM kind of pick the system, the modes that have higher participating factor to form the altered mode. Therefore, that reduces the entire equation that we saw before to a set of second order equation, which can then be easily solved. And that is the advantage of LEM. Now we can solve our equation. We can solve the system equation efficiently and faster. So now, as I said, if there's one change in mass or stiffness, if we are considering just one change, then that equation that we saw before, the equation of the system, can be reduced for stiffness change alone and then mass change separately. So the delta K matrix can be spectrally decomposed into alpha and tie matrices. And for the mass change also, that can also be done. So this entire equation can be reduced further into a set of second order equation, which can now be used to solve for the eigenvalue and eigenvalues of the new state. So this can be then done separately for stiffness added to the system or mass added to the system. So one of the very important part of this work, like about 90% of this work, was in the formulation of a solver to solve this equation. So majority of the work were done to like do this, and the initial part of this entire work was more on solving this equation efficiently and faster. So, and we're able to achieve that. The solver is online, it's on GitHub, repo, and yeah, it's available. It's been available for some years now for public use. So after we have been able to obtain the solver, we kind of now applied it in a very simple state on a simple system to like carry out state estimation. So the first thing to do is to solve the initial state eigenvalue solution. And for this simple work, we kind of modeled the beam with 5 nodes and then calculated the mass and constructed the mass and stiffness matrix using Euler-Bernoulli beam theorem. And then we solve for the eigenvalues and eigenvectors of the system, from which we can get the frequencies of this vibrating frequencies of the system. Now, after that, we need to introduce a change to this system, which where LEM comes in. Can we like track this change happening to the system with LEM? So we introduce a change to the system in addition of a roller support at node 4. And then you have to identify the change in mass and the change in stiffness matrix, which is here. The step 2 of LEM is to now spectrally decompose the delta K matrix into alpha and tie matrix to identify the exact change that you're imputing into the system. And the step 3 of LEM is to set the truncation, which we are now including only the contributing modes. So now we don't have to consider all the modes on the system. We can just consider the few modes that have higher participating factor. Now to the step 4, we can now solve our the set of reduced second order equation using the divide and conquer approach, the solver that I talked about that we formulated earlier. And then we compare this solver to available function on Python's, that's SymPy function subset on Python, and the results was very good. The comparison was good. The errors was very low, which kind of validate the solver that we formulated. Now, step 5 now is to use the eigenvalues that we computed here earlier to now obtain our frequencies of the system, which we can use to like, do our state estimation. So the generalized eigenvalue and LEM was now compared together because the generalized eigenvalue is like the base value in this entire work. We believe the generalized eigenvalue is correct, and then our work length, we compared all the results to generalized eigenvalue. And as you can see here in the for the first 5 mode of the beam, that was compared and between generalized eigenvalue and length, we can say that we have a very good tracking result between generalized eigenvalue and length, except for the fifth mode with some bit of differences. So this is the signal to noise ratio for the first four modes. Only the only difference we find is in the fifth mode where we have higher error. And the reason for the error is because we are using just 5 nodes to define the beam. If we increase the number of nodes, we are going to get a better increase, estimation, like frequency values, rather than this light error. So now the next thing we did was to do a timing study for the length approach that we just reformulated. We kind of timed each of the steps separately, and step 4 is the one with the highest timing, with about 0.33 milliseconds, I believe, which falls under the latency that we're looking at, 1 milliseconds. And then we also know that if we increase the number of nodes, the accuracy increases. So we kind of increase the number of nodes to about 30, and then we also study the timing again. And then the computation time to achieve 1 milliseconds in this first trial that we had was around 29 nodes, which is better than the initial prior work that was done at 23 nodes. So there was an improvement in this first work that we did. So now we went, okay, for this first work that we did, it was the solver was written in Python. So we kind of transferred the solver from Python to C. So it became better. Now we apply the solver on the one-dimensional system. And I'll just share the approach we used. So for the model updating process for the 1D system, it was separated into the experimental and the analytical. So for the experimental, kind of collected oscillation data, process it using FFT, and collect the frequency of the system. And then for the analytical part, there's a creation of surrogate model to define the cantilever plate beam, and then select some roller location, and then calculate the frequency. So the two frequencies from the analytical and experimental is compared together in order to now define, using this some comparison criteria, to now define the state of the system. So for the experimental part of this work, we use the drop-based experimental test bed. And how it works is that the roller moves along the beam, and then the accelerometer is used to collect oscillation data, as we're seeing here. This is the oscillation data. This oscillation data can be processed to obtain the frequency of vibration of the system, which can be used to track the roller position. So what we are trying to do basically is that we want to know where this roller is on this beam. Where exactly is it? We want to track it as it's moving. So that's what we are trying to do with this state. That's what we are trying to do with this experiment here. So in a simple term. So and then for the analytical part, we have to create a surrogate model that represents the beam analytically, and then we select a possible roller location. Where can the roller be on this beam? We select that, and we use that position to create to process our mass and stiffness matrices for the beam, and then we solve those mass and stiffness matrices to obtain the frequency of the system, and then we compare the frequency to the experimental part, to the experimental frequency, and then we kind of use those comparisons to determine if the roller is at the right location or not. Now, for the comparison criteria that we use for this work, we use the error minimization and the least square regression method. For some selected roller locations, we can select as many roller locations we want to try. That will determine the number of FEA models that we are having. So if you have more FEA models, the more computation and time it will take. But the more FEA models you have, the faster you're able to determine the exact roller location. So for the error minimization, it basically just select the roller location with the minimum error and frequency, and the least square regression uses the least square regression formula to select the roller location, the correct frequency for the roller location. So here is the result for a 21 node beam that we did. So we kind of modeled the beam with 21 node first, and for the generalized eigenvalue solver, here's the state estimation result, which is good. And then for the the result is very similar to the generalized eigenvalue solver, because the accuracy of both techniques is kind of similar. And then we introduce Bayesian search space to LAMP in order to using that to select a roller location. So instead of selecting the roller location randomly, the roller locations were selected using Bayesian search space. And we can see here that we have a much more refined estimation result for both error minimization and least square regression. Now, we also know that if we increase the number of nodes to a higher node, we have better estimation. So we kind of increase the node from 21 to 1, and upward. And then we can see that we have even better estimation as the number of node increases for both comparison techniques. And then the advantage of having a sampling technique in this work is that if we look at this first plot here, this is estimation without sampling. We can see that there's some kind of fluctuations in the tracking result. But then with the addition of Bayesian sampling, we obtain a much more refined tracking result. So Bayesian was very using the implementation of sampling technique is very beneficial for this work. Okay. Yeah, so now the next thing we did was the timing. We kind of timed the updating process for the three techniques we use: generalized eigenvalue, LAMP, and LAMP with Bayesian. And then as we can see, for the number of nodes we studied, 21, 26, 51, and 101, we had the two LAMP techniques kind of falls under the latency of 1 milliseconds. However, generalized eigenvalue after 51 nodes already shot up above 1 milliseconds, which is not really what we are looking at. But this result was similar for both error minimization and least square regression. So this is a much better representation of the timing, where we can see that LAMP increases linearly as the number of nodes increases. However, generalized eigenvalue increases like exponentially in terms of time. So when we look at it and we increase the number of nodes up to 250, LAMP is already performing about 125 times better than generalized eigenvalue, which is really impressive, way better than prior work that we saw. Now we also designed a more optimal model configuration. We look into designing and researching a model optimal configuration for the one-dimensional system. We set the error at about 10 millimeter and the iteration time at 1 milliseconds, the latency time we're looking into. And then the optimal configuration was obtained to be at 250 nodes and at 7 FPA model. So this configuration will kind of give us less than 10% and 10 error and falls under the 1 milliseconds timing. All right, so that's for the one-dimensional. We had a very good result there. We published it in Elsevier Mechanical Systems and Signal Processing. Yeah, so to the 2D application of the work, the first thing we had to do is to formulate the 2D system. Work. So I'll just differentiate between the 1D system and the 2D system. For the 1D that we talked about is there's just one in-plane deformation, just the X in the X-axis. But for the 2D system, we have two in-plane deformation and one out of plane. So we have the X and the Y. So it's a much more complicated system compared to the 1D. So now the 1D and the 2D nodal construction. For the 1D, we just construct the node along the just the X-axis, but for the 2D, we have to construct the nodes along both axes. So it's a much more bigger and then more complex system compared to the 1D. Now, the 2D model formulation that we used was we used the middling plate theorem to formulate the 2D plate used for this work, which superimpose the solid element onto the plate element to achieve the shell element itself. So this is a very simple 2D plate. with just 4 nodes. That's the simplest we can go. That's the simplest 2D plate with 4 nodes. And each node has 6 degrees of freedom. So unlike the 1D system whereby every node has 2 degrees of freedom. So on a very simple plate like this, where we have 4 nodes, this is 24 degrees of freedom. And compared to 1D system with 4 nodes, that would just be 8 degrees of freedom. So there is 3 degrees of freedom for the translational displacement and 3 degrees of freedom for rotational displacement on the 2D model formulation. So this is the technique that was used is already available in many finite element modeling textbooks. So it's just repeated here as the process that we use in formulating the matrices. So the steps are to construct the shape functions, then formulate the strength matrices, and then lastly calculate the stiffness and mass matrix for the system. So these are just the first step, construction of shape matrices. Okay, I'll just skip some of this. Then the second step, the formulation of strain matrix, that is the strain energy in the 2D and 2D element and 2D plate. And then lastly, the strain matrix and the shape functions can then be used to now construct the mass and stiffness matrices using these integration formulas. It's kind of a bit very computationally expensive to formulate these matrices, especially if the number of nodes that we are looking into is very high. So that's why we kind of use reduced models to define the plate. So now the next thing is to like build the global stiffness and mass matrices using the transformation matrices. As I said, the concept is available in many finite element textbooks, but that's what we use for the 2D model formulation. Then next, we went to the 2D implementation part. So the first thing we did was to validate the matrices that we formulated using main grid plate theorem. We use ANSYS to do the validation of the matrix. And we used the property of the plate was a steel plate with this dimension, a template 0.006 millimeter. And then we use 9 nodes, 2 configurations, 9 nodes and 961 node, which kind of represent a much perfectly meshed plate. And the plate was modeled in a free mode. So for the first simulation, which was the 4-plate element, we're able to only obtain the first 12 modes of vibration from the system because of the very badly meshed it was, how badly meshed it was. So the first elastic mode was seen at mode 7. And then for the second mesh, which is second configuration of 900 elements, so it's a much better refined meshing. So we're able to even obtain higher modes up to, I think it's way more than 19. And the similarities is that the first elastic mode also is seen at mode 7, which is similar to the 4-element plate. So we compare the frequencies for each mode, for all the modes together, for the 4-element and the 900 element, and the error is less than 10% error. So it kind of makes sense that we can use the 4-element plates to define the system rather than building matrices of about, I don't know how many thousands the matrix would be with the perfectly refined mesh. So we kind of go ahead and use the 4 elements to do our validation. After that, we build the matrices, the 54 by 54 matrices for these 9-node plates, and then we solve the eigenvalue solution using generalized eigenvalue. And we compare the FEA analysis, that's from ANSYS, to the generalized eigenvalue frequency for the 7 to 12 modes. And the result is kind of very identical with low amount of error. So this kind of validates the matrices that we kind of formulated. So now the next thing we did is to go ahead with single state change with generalized eigenvalue and LEM. Now we are introducing change into the system, which is the main core of the process, changes in the structure. And then we introduce stiffness change of about a very high stiffness change into the system from node 1 to node 9. And here is a result for the addition of stiffness from for each of the nodes from 1 to 9. and we compare the results, the frequency calculated from generalized eigenvalue to length, and also computed the error. And we can see from this result that we have very good correlation between length and generalized eigenvalue, which is something we've seen from even the one-dimensional state. So these also confirm the accuracy and validity of length algorithm for this work. So the next thing we did was to go ahead and do the timing and to look into the timing for this work. So we increased the number of nodes from 9 to about 169. And then as we can see here that the degree of freedom on the 2D plate is increasing because of the 6 degree of freedom on each node. And then the matrix size also increases accordingly too. So it is kind of going to get more difficult to solve the eigenvalue solution using generalized eigenvalue procedure if we are looking at like solving a very good meshed system. So now we also computed the frequency from generalized. Okay, this you have seen that before. The error is very low. I've showed that before. And this is the timing for both for generalized eigenvalue time and the length time. So we can see that length or generalized eigenvalue already exceeded the 1 milliseconds iteration time at around 16. Yeah, after 16 nodes, already exceeded that. However, length is still performing very well under the 1 millisecond time, even up to 121 nodes. So now here is this is a better plot that shows the results for the accuracy between generalized eigenvalue and length. We can see good correlation with low error. For the timing is very similar to the 1D system where the length kind of increases linearly. However, the generalized eigenvalues over time increases exponentially. But in this regard, the difference is that at 169 nodes, length is already performing more than 2,500 times faster than generalized eigenvalue, which is significantly like really, really good. So this is very good, especially now if we are now looking at even more complex system. Definitely length is more advantageous because for several reasons that I've listed before, it doesn't like solve the entire equation, it reduces it. It's only picks those important modes that define the system to like, solve the new state of the system. So after that, after we've been able to validate the timing of length onto the system, we went ahead to like try to find an optimal model to represent the 2D system, just like we did for the 1D. So we kind of tested out 9 nodes, 16, 25, 36, 49, and 69. And then we kind of created a mass matrix for each of these ones. And then we went ahead and modeled this in a free state first. So each of these reduced model, we computed the frequency of vibration for those configuration, and then we compared it to a perfectly meshed free plate, and we computed the error. So for the first one, for this free plate, the 9-node plate kind of exceeded the 10% allowable error for this work. So only the rest, 16, 25, 36 to 64 kind of matches or falls under the 10% allowable error. And then we also modeled the plates as a cantilever plate for all the reduced model and then compare them to a perfectly meshed cantilever plate. In this case, the 9 and 16 nodes was already out of the 10% allowable error. So we only have 25 to 64 in the allowable error. So here we can actually choose, since 25 is fine for free plate and cantilever plate, we can actually select 25, or we selected 25 for further processing because, well, it has lower, it kind of falls within the 10% allowable error that we are trying to like work with. After that, we created the mass matrix for the 25 noded plate. So this is a 25 node plate now. And then we constructed a cantilever plate from the free matrices, from the matrix of the free plate by adding a fixity at node 1 to node 5. So we added a fixity at the 6th degree of freedom to construct a cantilever plate for further analysis. So now we introduce local change into the cantilever plate that we formed with the matrix. And then we have already added fixity at node 1 to 5. And then we introduce local change at all the nodes on the system, the remaining nodes in the system. But we only introduce those local change at one side of the plate because the other one side is a mirror of the other side. So we can actually use the nodes on the right sides to like mirror the other side. So the frequency that is obtained from introducing change on the right side is also going to be the same as the frequency when we introduce change to the left side. So as I said, the change was introduced from 6 to 25, and we did that. So these are separate work, each of them, and we computed the frequency using generalized eigenvalue and lem, and we also calculate the error. And so just as before, it was good correlation between generalized eigenvalue and lem. And then that was done up to for all the remaining nodes anyway. And then we kind of collected the data from doing this. So the data basically, these are the errors from all the nodes for each modes from mode 1 to 15. So for each of the nodes, we kind of selected the modes that have the highest, the 3 mode with the least errors for each of these nodes. And then went ahead to count the number of errors, like the modes that performed better. And then from there, we found out that mode 7 kind of better represent the system because it has the least amount of errors when we look at the entire table here. So we can actually use mode 7 on a cantilever plate. We can just, when we are implementing LAMP, we can just search out for mode 7 instead of searching out the entire number of modes when we are solving, which will further reduce the computational time when we are solving for second order equation. So this is just a plot of mode 7 and the error. So all the error from mode 7 are less than 10% error, which works perfectly well with this work. And then next we went ahead to like do the timing study for the change. So we kind of did a single state change with the 25 noded beam. And then for generalized eigenvalue, the timing it took for a single state change is 9.01 milliseconds, while length is 0.43 milliseconds, which is faster than generalized eigenvalue, about 20 times faster. And then on the introduction of four change, generalized eigenvalue took about 36. The change are one after the other anyways. So that's 36 milliseconds, while length is 1.62 milliseconds. So that's about 22 times faster than generalized eigenvalue. So this is also still confirmed on the reduced model that we also created. So now to the conclusion of the work. Well, from the work that we did, we were able to develop real-time structural model updating framework using local eigenvalue modification procedure tailored for high-rate dynamic environment. And then we achieved milliseconds to microsecond level latency in structural state estimation, which kind of performed way better than general eigenvalue modification procedure. Also, we validated LAMP on both numerical simulations and experimental testbed, demonstrating robust performance under changing boundary condition and structural modifications. Also, we extended LAMP from the 1D system to 2D, showcases versatility across domains and scales. And this work kind of positions LAMP as a viable tool for next generation smart structure and edge-based monitoring system, which paved way for future adaptive control and damage mitigation strategies. So this work was supported and sponsored by the Air Force Office of Scientific Research, Air Force Research Laboratory, NSF, and University of South Carolina. Yeah, I think that's all my talk. Thank you. and anything else.